Well, hello and welcome to today's installment of the CFA Colloquium. I'm going to refrain from saying good afternoon because I feel like that would be taunting our speaker today, who is Professor Naoki Yoshida, joining us from Tokyo in Japan, where I think it's just about gone 6 a.m. in the morning.
Yes.
So thanks for joining us at this time. So Naoki is a professor of astrophysics in the Department of Physics at the University of Tokyo, as well as being a principal investigator at the Kavli Institute for the Physics and Mathematics of the Universe in Tokyo. And he may be known to many of you because he was previously actually a postdoctoral fellow here at the CFA. And even beyond that, I'm sure Naoki's work will be very well known to many of you, spanning as it does a plethora of research areas, including the formation of the very first stars, galaxies, and black holes in the universe, the epoch of reionization, as well as in cosmological surveys. And Naoki is actually one of the co-authors of the very first iteration of the very widely used gadget simulation code. And it is in this context of cosmological simulations that he will be speaking this afternoon. And an interesting fact that I learned off his website just prior to the meeting today is that he takes great pride in the fact that he's worked with students and researchers from all continents on planet Earth, except for Antarctica. So if anyone here can help him complete the set, that would be great. And in any case, I'll now hand it over to Naoki to present his colloquium on cosmic relic neutrinos and large-scale structure, nonlinear clustering, and the neutrino mass. So Naoki, it's all yours.
Thank you, Sonok, and thank you everybody for inviting me. It's nice. It's already 20 years since I left the CFA, and back then I have all good memories, and I also lived in Cambridge, so I liked life in Cambridge. So I hope our normal life will come back soon, and then I will be able to visit there physically. Okay. Still, I hope this online colloquium will be enjoyable, and I should make it so. Okay, I will share my screen. So today I will be speaking on a little bit specific topic of cosmic relic neutrinos, which might not be quite appropriate for colloquium talk, but the methodology part that will be really applicable to many other things in physics and in astrophysics, cosmology. So I decided to talk about this. And also the science content itself, I hope, are very interesting and pretty new. And so in essence, this bottom panel or bottom picture is the Fugaku computer, currently the world #1 fastest computer. And I'm going to use this to detect the cosmic relic neutrinos. And what do I mean? I will tell you how. Okay, the cosmic neutrino background, CNUB hereafter, is a generic prediction of the Big Bang cosmology. It was released about 1 second after the Big Bang. And currently, or in the present day universe, it has a sort of temperature. It should have like a Fermi-Dirac distribution, but if we define the temperature as such, it should be close to the CMB microwave background temperature. Also, the number density is comparable. And in fact, in the early universe, when the recombination happened, neutrinos were kind of occupying a good fraction of energy density back then. Okay, and since then, the relic neutrinos, they have been permeating the universe. We can imagine like just homogeneously as literally a background. But today I'm going to tell you that it's, there should be really like fluctuations and inhomogeneity, anisotropies, and so on. Okay. But in any case, in most of the standard cosmology textbook, the CNUB is just like this. Okay. Oops, how can I move around? The neutrinos, they are interesting particles. They are the minimalist. Neutrinos, they have zero charge, zero size almost, and possibly zero mass. Well, in fact, the last one, we know it's not true, but it's nearly zero mass, basically. In fact, experiments discovered neutrino oscillations for atmospheric and solar neutrinos. That was the topic of 2015 Nobel Prize in Physics. So these experiments, oscillation experiments, tell us that the neutrinos have a finite mass, but the absolute mass scale is still largely unknown. All we know is the mass difference as depicted here. And also, we don't even know, we know there are 3 generations of neutrinos, or even like 3 flavors. And this relative mass ordering, we don't know. Typically, for some reasons, standard particle physics and so on, we expect this normal hierarchy, simple ordering, but there could be other reasons to have this inverted hierarchy, like on the right side of this panel. Okay. So determining the absolute mass scale and possibly this mass hierarchy will be a very important topic, both in particle physics and cosmology. Good. Also, we know the neutrinos have mass. So if they have, say, the mass is, say, about electron volt scale, they can be a dominant component of the mysterious dark matter. However, we know since already 40 years ago, we know neutrino dark matter model doesn't really work. So if neutrinos are dark matter, the structure in the universe should look like this. Very smooth distribution because of their thermal motions. And only rare huge clumps like galaxy clusters distributed in this way. 40 years ago, this could have been a very good model of structure formation, but we know now, by now, the actual distribution of galaxies and matter in the present day universe do not look like this. So we know that neutrinos have mass, but they are not really dark matter. But this story somehow revived, and we now need to study how structure forms with the existence of the permeating Relic neutrinos. Okay, they are the neutrinos are also elusive, and I can nicely describe it like this. So this is the solar system. In some way, if we could fill this solar system with heavy lead like this, I don't know the total amount, but if suppose we could do this, then let the solar neutrino propagates. Nothing happens. Most of the solar neutrinos can actually escape, even if we fill the entire solar system with lead. Okay. Only if we do this 50 times in size. So if you fill the solar system with lead out to 50 times beyond the Pluto's orbit, then we can capture about half of the solar neutrinos like this. So they are really, really difficult. Even for these high energy neutrinos, it's very hard to detect directly. However, researchers are clever enough to do some experiments or to do some measurement, and the current status of the measurement or constraints on the neutrino mass is summarized like in this slide. Okay, from particle experiments, we know the mass of the anti-electron neutrinos. It's about less than 1 electron volt or so. This is from Catalina experiments. Impressively, from cosmology, we can place a tighter constraint on the total mass of the neutrinos, like about less than 0.1 electron volt from mostly CMB Planck data. So this is like a battle of the particle experiment and cosmological constraint. On the red corner, we have these particles, and then on the blue corner, we have cosmology, basically. And the future sensitivity, the next round will be very interesting. In the future, both particle experiments and cosmology constraint will be approaching down to 30, 40 milli-electron volt. So when perhaps we will have a good hint on the mass hierarchy and also the possibly the precise measurement of the total mass of the neutrinos and so on. Okay, particle experiments. The 2019, the Catalina experiment, it utilizes the tritium beta decay as depicted on the left upper panel. Still, of course, directly detecting the new electron neutrino is very hard. So instead, using this huge chamber or spectrometer, it measures the emitted electrons, decay products, especially their energies. Okay, so this is for that measurement, this one is we need this gigantic apparatus like this. So this is on the detector is on the way to be installed at Karlsruhe and in some German town. I don't know if it got stuck or how they managed. And interestingly, some people are around completely ignorant of this event. But anyhow, this is the size of the instrument. The result is beautiful. This energy measurement, energy spectrum of the emitted electrons it just reminds me of the CMB experiments. Here, the error bars are 50 times enlarged, emphasized. Okay. So one can draw a best fit curve, the electron energy distribution. And as you know, this the overall shape or the endpoint feature will be really depend on the electron neutrino mass. So if the neutrinos are really massless, the endpoint curve should be really smooth towards zero like this. But it has some finite mass, it should end like this. And people want to really discern this difference or detect this feature. And the current sensitivity is about 1 electron volt. But the upgraded experiment will go to sub-electron volt and so on. That's the terrestrial or particle physics experiments. Cosmology, we do completely different thing. Okay. We measure the effect of the Relic neutrinos, much lower energy ones that permeate the universe, but they cause some effect on structure formation or matter distribution. So this is the famous large-scale structure, and one can calculate the matter power spectrum from this. Well, for now, I assume the galaxy power spectrum is it's just a tracer of matter power spectrum. Okay. So if we add a little bit amount of neutrinos, or as a function of total neutrino mass, as shown in this plot, the matter spectrum looks slightly different. So difference is, one can say, with current precision cosmology, one can say this is a large difference. But still, one needs to measure all the power spectrum for a wide range of wave numbers, and then to discriminate this power amplitude and so on. Well, this is for illustrative purpose. This goes from 0 mass to 1 electron volt, but in reality, we are dealing with, say, 0.1 or even 0.05 electron volt difference, and so on. One can do a similar thing for other, say, tracers or matter density measurement. The essence is, since neutrinos are moving very fast, actually in the early universe, it's close to the speed of light, they cause collisionless damping or free streaming. Okay. So the characteristic wave number or length scale is given by this, with the typical velocity dispersion given by this. So roughly 100 to 1,000 kilometers per second, they are moving. Okay, and they cause the collisionless dumping because the neutrinos also are coupled gravitationally with other matter. Okay, and then as I already showed, this dumping effect is directly determined by the total sum or total energy density of the massive neutrinos in this way. Okay. So observationally, we have a good prospect to detect this difference. Well, there are of course many systematics and so on, but theory-wise, we just need to do accurate modeling. Okay, say beyond linear theory or even beyond perturbation theory and so on. All we need to do is to get the accurate distribution of neutrinos and its statistics. Good. Just supplementary material. One can do the same thing using CMB and CMB lensing and so on. Again, if we take this CMB lensing, essentially the matter distribution at slightly distant universe, the difference is very subtle. Again, from massless neutrinos to say 0.3 electron volt. But one can have a hope to detect this small difference in many experiments in the future, or I would say in the near future. All right, so far I have been talking as if the C nu B is literally a homogeneous background, but since they have a finite mass and they interact gravitationally, they have, say, density fluctuations in the present day universe. So this is one snapshot from our own simulations. The left side is ordinary large-scale structure called dark matter distribution. The right side is corresponding neutrino distribution as simulated on the computer. Okay, it's not smooth at all. We really see the clustering around the high density regions and even like void regions. Although the relative density difference is small, but the fluctuations or inhomogeneities or anisotropies, if we look at from the Earth, there exists for these Relic neutrinos. Okay. More interestingly, this is like a preview of our simulations. We can also define the neutrino temperature like this, and we found, the temperature fluctuation is, say, noticeable or maybe not significant, but we can notice a temperature difference, say, depending on the place to place in the universe for this 100 megaparsec size. There are like hot spots and cold spots for Relic neutrinos. And interestingly, for this model, in galaxy clusters, the galaxy superclusters, the Relic neutrinos, they are colder than the cosmic mean. So I will talk more about these features later in my talk. Okay, so let's see how we got these nice results. Okay, the basics of the neutrino dynamics is fairly simple, I would say. Its dynamics is described by the collisionless Boltzmann equation using the velocity distribution function and coupled with the Poisson's equation. Here, the Poisson equation density should include everything else, like dark matter or ordinary matter and so on. But anyway, only these two equations. So in principle, for given initial condition, initial distribution of matter and neutrinos, the evolution of the distribution function should be followed in 6-dimensional phase space. 3 positions, 3 momenta, coupled with Poisson's equation. So in principle, this should be straightforward. However, as you can easily imagine, 6 dimension is really like a nightmare. Let's see, only computing wise or memory wise, if we store the distribution function f on 64 to the power 6 grids, it already needs 270 gigabytes memory. if we want to do more realistic, on 512 to the power 6 grids requires 70 petabytes memory. That is about 7 times of the total memory of the Summit, the US #1 computer. So this is certainly a nightmare. But simulations with 512 cube for positions and 256 cube for velocity or momentum can be actually performed on Fugaku already. So what is Fugaku? Fugaku is now in its full operation. It's a full-scale operation. It has 158,000 nodes and 52 cores per node. And its peak performance is 400 petaflops. This is currently the fastest. Indeed, since last year, Fugaku computer has these #1 in these major 4 rankings in supercomputing. Oh, by the way, Fugaku is another name of Mount Fuji, as given here. So this is the most powerful computer on this planet for now. Okay. Now, we want to run cosmological simulations. And so far with the limited early access system, we were able to run this size. So we configure 384 cube grids and 64 to the power cube for momentum and so on. Some of the initial result I have shown already. So we run a Boltzmann simulation in 6D with varying the neutrino mass, and we try to determine precisely the statistics related to the density field and so on. Okay, and then to see the effect of Relic neutrinos and Relic neutrino mass. Okay. Before going more in detail about the result, I need to explain a little bit of the, say, computational or theoretical background. So if we want to run cosmological simulations, many of you might wonder, why don't we just do the usual particle simulations? Okay, there are many people doing n-body simulations, and it should be straightforward to do so, including neutrinos. And in fact, many people do it. However, there are a few serious problems, as I see, and I want to illustrate a few examples. Okay, here I'm showing a simple picture. Later on, it's going to be a movie. Okay, so it's a simple merger of 2 systems, say 2 galaxies or 2 star clusters. Left one is by the conventional n-body simulation. The right one is with a direct Boltzmann solver. Okay, the respective resolution is very different indeed. Like, for n-body simulations, for this simple system, I use expensive 2 million particles. But for direct Boltzmann, I could only use 64 to the power 6 grids. Okay. So this is simple near head-on collisions. The outcome is easy to expect, guess, like this. First encounter, it gets separated. I apologize, this is very boring, perhaps. Okay. and also, this is the only one movie I can show today, so I feel even like ashamed. But this is very interesting, actually. Okay, so overall it looks okay. That's why people, including me, do many particle simulations for gravitational dynamics. If we look at the velocity structure, it's very different. Since this is near head-on mergers, there should be a clear, say, bimodal velocity structure in this velocity space, Vx, Vy, if we take one point. And our Boltzmann solver, the result is like this. And if sometime after, it looks like this. One is incoming, the other is outgoing, something like this. If we look at the same thing for 2 million particle simulations, the velocity distribution looks like this. Okay. Please do not get confused. The particle positions, the particle distributions are in velocity space, okay? Not in the configuration physical space. And if we try to smooth this out, we can barely see this large hub, but basically no structure in it. So it's miraculous, I would say, or curious, you know. Usually we feel 1 million particles per body is like high resolution enough. And we think we represent the system correctly, but in velocity space, it's not. If we take the velocity power spectrum, our Boltzmann solver shows this smooth velocity power spectrum. But for particle simulation, we see this floor. This is basically shot noise. So with this shot noise feature, one can easily calculate. In fact, we need a near trillion particles for these simple simulations to reproduce this velocity structure and so on. So this is it. But as I showed, and as you can imagine, that the outcome, in the configuration space distribution look totally okay. So this is almost like a mystery. And one deep question is, so if this is true, if what I showed are really true, are usual dark matter simulations okay? One can wonder, but they are actually perfectly okay, basically. If I have time, in the end, I can discuss more. But anyhow, this shot noise is really a bad thing, especially for the thermal relics or hot component in numerical simulations. Okay, I can illustrate it. So again, back to this cosmological simulations with massive neutrinos. Here I show the neutrino distribution, density and temperature for 100 megaparsec box size. The left side, Boltzmann solver. The right side with ordinary particle simulations. As you can see here, one can do reasonably good for, at least for density, if we employ kind of craziest number of particles, 1500 to the power cube, representing the distribution of massive neutrinos. But if we want to know the temperature distribution, the result looks really bizarre like this. Okay, it's really no way to discern the temperature difference. It's just noisy. The particle noise really hampers to measure this temperature distributions. Whereas, as I showed already, we have, because we have the full phase space information in 6 dimensions, we can reconstruct this effective temperature in this way. And we see this temperature difference following the large scale structure of dark matter, basically. So this is a reason why I took a long way to get this kind of simulation done, instead of just increasing the number of particles. You can also imagine the accuracy of this particle simulation scales only with square root of n. So 10 times more particles, only 3 times or so better. So it's kind of, I would say, almost miserable to ever increasing this number of particles for this particular purpose. Good. The next part would be a little bit technical details. So I just basically scan through, I almost skip. Basically, we took the modern technologies of computational physics to do the simulation, especially in a cosmological context. But some basics, again, the physics behind it is very simple. In 6D or even in 1D, we just need to solve this hyperbolic transport equation, advection equation. And this here, 4 star. is just a gravitational force. So this corresponds to, if in plasma physics, this corresponds to the electrostatic plasma problem. So, but the point is, we need to do this advection in 6D for XYZ and UVW for velocity component and so on. Again, I feel like skipping many of these. If say some of you would be interested in, I'm happy to spend say hours on this. But basically, we did many tests for this new scheme to follow the motion of thermal particles or the neutrinos. So this is simple collisionless damping simulations, the perturbation evolution. Here, I often show this X and V, like phase space distribution. And depending on the perturbation wave numbers, it can, the perturbation can dump or can be unstable. And this critical wave number, I showed a little bit earlier for the neutrino effect for the structure formation. Let me skip again. And this is like, you know, I'm sure to most of you, this is unimportant. But just briefly, we need higher order reconstruction scheme for numerics. Because in the end, we need to follow the fine structure in phase space. Again, this is the phase space X and Vx. From the nonlinear Landau damping test simulations. And as you know, because of the nature of the collisionless system, the initial phase space structure should be preserved like forever. But if we employ the low order scheme like PFC here, the phase space sheets are completely smeared up. But if we employ 5th and 7th order higher accuracy scheme, we can preserve this fine sheet structure in this experiment. Okay, and in the end, we decided to use 7th order scheme to do many other real applications. Okay, in cosmology, we need to modify a little bit, you know, because the universe is expanding. So in the spatial coordinate, we should have the scale factor, and we have also a canonical momentum and so on. But the rest is simply, again, the advection equation in multi-dimensions coupled with Poisson equation. So for our simulations, we use a hybrid Boltzmann or Brazov n-body solver. We do the Boltzmann simulation for hot neutrinos, but we do the usual particle mesh calculation for cold dark component. In this way, we can follow the dynamics for both dark matter and the neutrinos pretty accurately. And these two components are coupled via the Poisson equation. Okay, cosmology, the standard ones, we vary the neutrino mass and to see the effect of the on the matter power spectrum, basically. Okay, hereafter, I really like, you know, looks like a machine gun talk. Like I show one by one the many preliminary or like already published results. First one is dark matter distribution. Nothing impressive. We have seen this many times. Corresponding neutrino distribution, we see the clustering around superclusters like this. On this, the side length is 200 megaparsec. Okay, so this contours a dark matter distribution, basically, galaxies and galaxy clusters. And we see this sort of hump or large-scale over-density region of Relic neutrinos. Dark matter bulk velocity field, I indicate the velocity field by ticks like this. So you see the inflow of the matter toward the high-density regions. Okay. We can also calculate the neutrino bulk velocity field, the magnitude depicted in color like this. Okay, so this bulk velocity difference will become important later in my talk when we calculate the so-called neutrino wake. Okay. Velocity structure, again, this is a comparison with logarithmic scale. This is the two-dimensional slice in the velocity or momentum space, the distribution of neutrinos. with color scheme is our solution. We see this nice tail. Basically, it's like a Fermi Dirac, but we also see this, let's say, deformed shape at low energies, low velocities, due to the bulk motion of the Relic neutrinos. You can also think this as the C nu B background anisotropies if we look at from the Earth or from the Milky Way. So the surrounding or incoming neutrinos should have this kind of distortions on the angular scale for low velocity component. For high velocity component, it's like nearly spherically symmetric. Okay. Oh yes, and then these particles are the realizations from particle simulations. So again, we see it's impossible to discern the distribution function features with these particle simulations. Okay, like this. Shown. Let me skip this. It's essentially cause sampling will cause a big problem for determining neutrino temperature, neutrino distribution, and so on. Okay. Relative velocity between CDM and neutrinos. This is interesting. Very peculiar patterns. So we found from our simulations this the magnitude of the relative motions is close to a few hundred to 500 kilometers per second or so. The coherence length is 10 megaparsec scale. Okay. And in fact, the relative velocity is mainly contributed by the bulk velocity of dark matter component. So when a galaxy with its dark halo is moving, then that is the main source of the relative velocity. But the rest, the neutrinos are really moving like coherently over 10 megaparsec scales. Okay. Now the damping of matter power spectrum, so density distribution. So this here I show the residual or difference between the case with zero mass neutrinos and with massive neutrinos. When the neutrino, the total mass is 0.2 electron volt, the power spectrum damping is like this magnitude, about 15%. So these are our simulation results with different box sizes. In the present day universe, it looks like this. Okay, so for this 0.2 electron volt case. Other cases from smaller mass to a larger mass. For larger mass neutrinos, this damping is larger, basically. Okay, and we find this typical spoon feature for this relative, let's say, the ratio with respect to the zero neutrino mass case. Okay, redshift 0 and redshift 1. And we can compare the linear theory or perturbation theory. Let's take this pink curve. The perturbation theory prediction is this dashed curve. Obviously, it's limited to linear scale, say only to k or 0.03 or so. Our solid line extends way over to 10 inverse megaparsec. And interestingly, these dotted lines are from the halo model. It's a combined linear theory and quasi-linear transition and the nonlinear component as described by essentially one halo term, so-called, kind of the dark matter distribution within a single dark matter halo. So this analytic model calibrated by previous simulations are doing very good, actually. I'm sort of surprised, this spoon feature and also the depth and also the point where it takes a minimum, it like really accurate. The only one difference is in the intermediate nonlinear scale, which we believe ours is more accurate. But overall, this relatively simple analytic model can capture the essence of this damping effect for redshift 0 and redshift 1 and so on. Okay. Mass function of dark matter halos, basically the galaxy clusters abundance. The difference is small, but there are some differences basically. As a function of the Relic neutrino mass from 0 to 0.4 electron volt. So usually for rich galaxy clusters, 10 to the 14 solar mass, we see the dumping or suppression of about tens of % level. So future galaxy cluster surveys, X-ray, lensing, even optical, they try to get this cluster abundance. And if the result is precise enough, and also this is like a model dependent, but one can determine the neutrino mass by measuring basically the abundance of galaxy clusters. Okay, interesting statistics we found was there is a tight correlation between the galaxy number density and the local neutrino overdensity in this way. So the horizontal axis is the galaxy number density. Essentially, we use dark matter halos. The vertical axis is relative neutrino overdensity. So there is a nice correlation between the two. And this correlation itself is dependent upon the total neutrino mass. So once we know the absolute mass scale for the neutrinos, one can infer the local neutrino mass from basically from the local number density of galaxies in this way. And we derived all these coefficient correlation and so on from our direct simulations. Okay. This is still like futuristic. If we could measure the effective temperature or local velocity dispersion, there's an interesting effect. You might think, neutrinos are trapped in galaxy clusters, a large dark matter halo. Their neutrinos might be hotter. Actually, if hotter or colder depends on the absolute neutrino mass, basically. For massive ones, they are hotter in galaxy clusters. But for realistic small mass cases, neutrinos are colder compared to the cosmic mean. So depending on the neutrino mass or neutrino velocity dispersion, this is a competition between the escape from the large, deep gravitational potential well of galaxy clusters, or the trapping of low energy neutrinos within the galaxy cluster and so on. So this transition point is around 0.2 electron volt. Of course, from a variety of observations so far, we know likely the total mass is below this. So basically, neutrinos in clusters are colder than the mean. Finally, this is a very peculiar effect, but will be a decisive signature of the Relic neutrinos. So suppose, of course, the neutrino is permeating the universe like the nearly homogeneous component. So the galaxies or dark matter halos are moving in the sea of neutrinos. And then the galaxy or its halo will see the wind of massive neutrinos. And behind that, so now this galaxy halo is moving downward. It feels the wind against, neutrino wind against. Then as a back reaction of dynamical friction or vice versa, there should be a wake of neutrinos or some hump of neutrinos in this way. Okay. And as I showed, the relative velocity or relative motions are caused between the dark matter and the neutrinos. So always behind galaxies or galaxy clusters, there should be a very small or tiny little hump of neutrinos. Inversely speaking, dynamically, the existence of this small neutrino hump is causing the dynamical friction for the galaxy or galaxy halo. So how we discern the effect? First, we do these theoretical calculations, and for the first time, we could see the clear signature of neutrino clumping behind dark matter halos. Okay, so suppose dark matter is sitting here, moving always downward. So the coordinate is aligned as such. depicted on the right. So we have the relative velocity between the dark matter halo and neutrinos. And as a function of the relative angle of this velocity vector and say the configuration space, we depict the over density of neutrinos in this way. And then we see, of course, the unrelated or like the forward regions, the clumping is essentially there's no clumping, but right behind the moving object, there is a clear hump with this level, the enhancement of neutrinos. Okay, so of course, because of this elusive nature of neutrinos, it's very hard to detect, go there behind the galaxies, the galaxy clusters, detect them. It's very hard, I can imagine. But they are on large scale, or in the real universe, there really should exist this kind of neutrino wakes generated. And if detected in the future, this is really the decisive signature of the existence of light thermal relics of neutrinos in the entire universe. Also, okay, this is again, of course, futuristic, but let me be brave enough. If we can detect this signature, one can, of course, discern the total neutrino mass. But I don't know when, in the time when we can really detect this signature, the total mass is already known. But anyhow, this can be also as say a feature or a statistics one can use to determine the property of Relic neutrinos. Okay, even more brave I'm becoming. There are some possibilities in the very ideal case if we have two populations of galaxies, light one, heavy ones, or like even maybe blue galaxies, red galaxies, and so on. If we take the distribution cross correlation, there should be a cross term between the two populations appearing. And with introducing bias parameters, one should be able to discern this cross correlation, dark matter, neutrinos, and so on. And we should have the angular dependence. If we really know perfectly the motion, the relative motion of dark matter and the Relic neutrinos in this way. And by doing the cross correlation and angular difference with respect to the line of sight and velocity component, again, one can discern the effect of neutrino wakes in this way. Okay. Well, again, this is going to be quite tough to represent with ordinary particle simulations. It's going to be just noisy. I could see this clear signature only with the novel velocity, the Boltzmann technique. Okay, the result is that's about it. The future cosmology, we expect many large surveys would be delivering huge data. Vera Rubin Observatory would observe the order 10 to the 10 galaxies in essentially half sky. Combined with the CMB measurement, temperature polarization, CMB lensing, and so on, we can do well. So here's a plot from your local colleague, Harvard product. Cora Dworkin and her colleagues, they say the absolute mass scale will come down by combining LSST or Vera Rubin Observatory Survey and CMBS4. The sensitivity will come down to, let's see, I don't know, 30, 40 millielectron volt in the future. We also have other instruments like Subaru spectroscopic survey for high redshift universe, or later in this decade, Nancy Grace Roman telescope for more precise galaxy surveys, both for galaxy distribution and lensing. Okay, particle experiment side on the red corner, there are proposed experiments like Project 8. This is a neat idea of using cyclotron radiation spectroscopy to get this electron energy more precisely, which will enable the determination of the anti-electron neutrino mass down to with a precision of 0.03 electron volt or so. There are many ongoing and proposed neutrino-less double beta decay. All these terrestrial experiments will tell us about the neutrino mass, Dirac or Majorana mass term, and so on, mass hierarchy, and so on. And finally, Hyper Kamiokande under construction in Japan. It's basically the monstrous Kamiokande neutrino detector. I can finish my talk with this spectacular slide. So Hyper Kamiokande is now free approved. Construction ongoing. It's basically a huge 100-meter tank, and basically it can detect, say, high energy neutrinos from the sun, from elsewhere, and so on. The science goals are, again, neutrino mass hierarchy, lepton sector CP violation, proton decay, or confirmation or validation GUT, and so on, and so on. One, well, dreamy thing is if a supernova goes off in our galaxy, say at a distance of 10 kiloparsec, this Hyper Kamiokande detector will detect of the order, say, 60 to 100,000 of neutrinos. And by looking at, basically, with the good energy resolution, the time evolution of this neutrino count by Hyper Kamiokande, then one can infer the normal hierarchy oscillation feature or inverted hierarchy oscillation feature with these fine details with number counts. Okay, so after 2027, maybe we are waiting for Betelgeuse to explode, to enable. Well, when we or at CFA, when Betelgeuse really explodes, then we do many other things. But one certain thing is that with neutrino detectors, one can do this precise measurement, and one can know the absolute mass scale of the Relic neutrinos, or neutrinos basically. Good. Thanks for listening my talk, and this is a summary. Basically, I saw very theoretical calculations to be used, I hope, for future cosmological constraints. And the one thing particularly I should notice or mention is, again, this application is not limited to only cosmic Relic neutrinos. I can foresee many interesting things like baryon dark matter models such as warm dark matter, Bose-Einstein condensates, and so on. Nowadays, many people are fascinated with these ideas as an alternative to the usual cold dark matter. Like fuzzy dark matter too, we do need precise peculiar velocity features, and our technique would be very useful. And even, say, to space plasma, to galactic dynamics, there are many interesting things in astrophysics that needs the precise and accurate account for the collisionless dynamics of dark matter and the stellar component. Okay, thank you for your attention. And now the sun is rising, so I see a bright sky, and it's a good time to have your questions. Thank you.
Thank you very much, Naoki, and I'm glad your day can finally get off to a start now that the sun's risen. Fantastic. So I think we have time for some questions. So if people, firstly, give you a virtual rounds of applause, and subsequently you can use the raise hand function on Zoom to notify me that you have a question. Depending on which version of Zoom you have, it may be under participants or it may be under reactions. So raise your hand and let me know if you have a question that you would like to ask now, okay? While we are waiting, I might just take the prerogative and ask one myself.
Thank you.
So you showed very convincingly that there are these nice applications that come out of these Boltzmann integration techniques, such as the neutrino wakes and so on. But in a similar vein, I wanted to ask: are there certain predictions that have already been made with particle-based neutrino simulations that you think need to be revisited as a result of the particle-based approach? If, say, the configuration space side of things is fine, but are there other things you think might actually be incorrectly predicted?
Incorrectly is a big word, but so like, interestingly, no catastrophic failure we found so far, except in the say the practical. So like, are you still seeing this
Yep.
slide? Okay. So I showed this semi-analytic modeling of this power spectrum. It's basically developed analytically but calibrated against the existing particle simulations. So basically they do well in this thing. Only I feel is I want to have more accurate things like this, even this nonlinear enhancement or like this depth and so on. Velocity space, I know it should be completely different. For some reasons, this velocity space difference do not appear to affect the ordinary statistics we are concerned with. But so like, let me show, perhaps maybe not right now, but at some nice point, I want to discuss with you or with a few other people maybe. Actually, this has been a mystery for me for a long time. When the velocity space is like this, the particle dynamics still look okay, and physically I don't quite understand it basically. But I don't know. I have three theories, but I'm happy to be elaborating more. But perhaps this is like too much in detail. Okay, so.
Fantastic. Yeah, it sounds like something definitely worth discussing. All right, so I see Volker Springle has raised his hand. So Volker, would you like to ask your question?
Yeah, thanks. Naoki, hi.
Hi,
Nice to hear you. Yes. Actually in Europe, and here it's late at night, but thanks for this great colloquium. I wonder about the case when the neutrinos are very light and still relativistic. And it seems that the treatment of the gravitational field is still Newtonian in this case, right? Are you concerned about this? I mean,
yes. Okay. Our immediate treatment was simply we started all these simulations. Let's see, whichever. All these simulations from low enough redshift so that the neutrinos became non-relativistic. But if we want to do more very accurately, we need to treat relativistic species more accurately. And the real GR effect should be taken into account, especially for, say, 1 gigaparsec or few gigaparsec volume. So that will be next, say, direction. Also, your question also prompted me to answer this. Next thing we can do with Boltzmann solver is this simulations with two generations, the two neutrino species. We know there are 3 mass eigenstates, and for the simulations today, I treated them equally, but there should be mass difference and so on. So if we treat 2 neutrino species separately, respective velocity distribution functions, the outcome will be different again. I can even imagine one species highly clamped, the other is like really homogeneous and so on. Again, most of the results could be like, academic or theoretical, but there should be really such differences.
Okay, thanks.
Yeah.
Great. So the next question is from David Hernandez.
Hey, yeah, I really enjoyed the talk.
Thank you.
Yeah, I was going to ask about what kind of challenges, if you could talk about the challenges of solving the Blasov equation. Like one thing I was thinking about is if the streams can become too thin, is that an issue?
Oh, yes. Yeah. It turned out it's a technical part. Sorry, I skipped mostly, but there are many things. to get everything correct. In fact, I would say it took for us about 10 years from the idea of doing this and to all the way up to the things correctly. The say fine phase space structure in multi-dimensions is one case, and even for linear evolution, for some time we struggled a little bit, and because of the overall inaccuracy and velocity space, we need to represent smooth enough and so on down up to the some of the problems we need to represent high velocity data very accurately, and things like this. So it's all like a collection of modern techniques, not really like particularly one thing. Of course, memory wise, we really need a huge memory and CPU time too, but only recently it really became realistic or feasible, basically.
Great. Okay, Gus, would you like to ask the question next?
Yeah, thanks, Naoki. This sort of distinction between the Vlasov and the typical particle way of solving the Boltzmann equation is pretty reminiscent of like the Eulerian versus Lagrangian sort of perspectives on fluids. And in the case of Eulerian, there's a lot of these like techniques that have been developed, like AMR or even like a moving mesh in order to deal with large density contrasts. But it seems like the simulations you ran were all fixed grid. Do you think applying something like that to this case would be helpful, or is like the density contrast not too high for it to really matter?
You're absolutely right. So we started from this uniform grid in velocity space and so on. For simplicity or for as a starting point, we certainly think about adaptive mesh refinement or like adapting discontinuous Colloquium method and so on. But only one thing we didn't do is like in the really free nonlinear regime, like Milky Way halo. What is the phase space structure for dark matter component? That's currently we can't do because of this basically complexity and so on. But I'm hoping by adapting even more modern technologies, one should be able to do this. And what else? I wanted to say something else, but anyhow, that's sure. But it's simply technically involved, but it's conceivable to extend this method. So that's a good direction technically.
Thanks.
Great. And Naoki, we'll take 2 more questions if that's okay with you.
No problem.
There's one in the chat, but I'll go to Ramesh first.
Okay.
Hi, Naoki. Ramesh here.
Hi, Amin. Hi.
Great talk.
Thank you.
So, you mentioned that you use 5th order or 7th order reconstruction method, and it makes total sense because you have a 6th order grid. You can't increase resolution without paying a lot. So the way you get accuracy is by going to high order. My question is, when do you stop? I mean, should you go to 9th order or 13th order? Is there a simple, way of deciding how high you should go, and when do you stop benefiting?
Very good question, Ramesh. We never stop, like Gus asked before. But let me see, Ramesh, my choice was on a practical basis, on practice basis, meaning when things came out okay with respect to the linear analysis for the linear regime, and also for when the overall matter spectrum for many other cases, the growth of these density fluctuations on the linear regime became okay or accurate enough, we stopped at 7th order. And it simply becomes more complicated, and the gain is small for at least for cosmology purpose. But real plasma problems and so on, honestly, I don't know. Maybe we should go like higher or more fancier technique, or mesh refinement and so on. Sorry, this is
Yeah,
really
yeah.
like only for
thanks. That's very helpful. The thing is, in some problems, because there are shocks,
yes,
which cause you to decrease the order, there's no point going too far, but you are completely collisionless. So you can go as high as you can get a benefit. So
yes,
and of course the programming, that will get more and more complicated.
Yeah, absolutely right. Yeah.
Thanks.
I'm happy really to try the more fancier method and in the near future. Thank you very much.
Brilliant. And we have one final question in the chat. So it first says, thanks for the amazing talk. Could you elaborate why would light neutrinos escape clusters while heavy neutrinos would get stuck in clusters?
Very good question. This is like counterintuitive basically, and I was happy to see the result. That again, this is kind of confirmation that we do things okay. So suppose the fact that we have the momentum or velocity distribution for the neutrino component, meaning you can imagine this part in the velocity space, they have small velocities, even less than 100 km/s. They can be gravitationally trapped by even the Milky Way halo. Okay, so it's like preferentially the low energy neutrinos can be trapped in galaxies and galaxy clusters. By the way, this can be profound implications for like direct Relic neutrino detection. But anyhow, so thing is, galaxy clusters grow in mass, in velocity, say essentially from say 100 to 1,000 km/s, whereas Relic neutrino velocity scale drops as a function of time. So there is a crossover point depending on the neutrino mass, and that crossover point is around 0.2 electron volt, or depending on the redshift actually. So afterwards, in this region, only the low energy portion can be trapped preferentially in galaxy clusters. Hence, with respect to the other mean or ordinary regions, it's actually can be colder. Whereas the other thing, this is like a sort of usual visualization. The big potential well, deep potential well can capture even like high energy ones. That's the main reason. And this is very nice to see. Also, again, not directly detectable.
Brilliant. Thank you very much. All right. Well, I guess. Whoops. There's another question that's come up just in the 11th hour. So could you explain why, in the plots of the ratio of the power spectrum with non-zero neutrino mass at the zero mass case, the scale of the dip decreases at smaller redshift? Is it just a consequence of expansion?
Both evolution, but maybe the vertical scale was different. Let me closely see. This is all like relative sense. So I need to check if I did both panels. The scale is correct, but this is only like normalized by the respective case. So let me see.
Yeah, no, sorry. I mean the position, the scale, the value of k.
Okay, this.
No, sorry. No. Okay, I thought it was counterintuitive. I read wrong. So at smaller z, so 0, the scale larger. So okay, makes sense. Yeah.
Yes. Okay.
Just the consequence of the expansion, right?
Yeah. Good point. I should have really mentioned. Okay, thank you.
Okay, brilliant. So now I think we can all thank Naoki for giving his talk once again. And I'm sure everyone is applauding vigorously within the confines of their own Zoom rectangles. But thanks a lot, Naoki, and we hope that you'll be able to come visit us again at the CFA at some point in the future.
Yes, thank you very much. Thank you. Okay. Have a good evening.
Cheers. All right, thank you, everyone. Goodbye.
Bye.